Good morning, everyone. If you cannot hear me clearly or something, please let me know. I'm Victoria. First, thanks to all of you for coming, and thanks to Daniel for inviting me. So today I will speak about the quantum game of life. Maybe the title is a bit confusing for you, but hopefully you will understand what I mean by that. So as Daniel was introducing me, I was born in a small village in El Pinós, in Alicante. Then I did my bachelor's in physics here at Universitat de Valencia. My supervisor was Vicent Jiménez. Maybe some of you know him. Then just after finishing my bachelor, I got a grant to go to Germany for 2 months in Darmstadt. It was a very, very nice experience, so I would encourage you to apply for those kind of things, for programs for undergraduates, or if you're graduated, to apply for grants. Apply for everything. That's my advice. So then, when I finished in Darmstadt, I came back So I came back to do my master's in theoretical physics at Universitat Autónoma de Madrid. It was 1 year. So after I finished, I was a bit tired of studying, as many people, I guess. So I decided to stop, and I got a job in Barcelona, programming. It was not too bad, but I didn't fully enjoy it. I was there for 9 months. And then I decided that I wanted to pursue a PhD. So I came back home to work on my applications and to rest as well. After some time, I managed to get funding to start my PhD in Ireland, in the National University of Ireland, Galway, since October 2019 until now. And maybe, I don't know, but maybe you would know Galway because there's a song called Galway Girl by Ed Sheeran. You should check the video. It's fully shot there, so you can have a flavor of the city. It's a very nice city, but it rains a lot. You need to get used to that. Okay, so, and 1 month ago, I was also given a grant to go for a month to Paris at Sorbonne Université. It was a very nice experience. Again, apply for everything. So I came back, and what I'm trying to say with all of this is that life is non-linear, if you know what that means, but it's okay to just move forward and back. It's okay to hesitate on what you want to do, but yeah, you will find out at some point. So I said I'm doing my PhD currently in quantum games. Maybe you don't know what that means. I didn't either before starting. But let me tell you a bit about games. Game theory is a field in mathematics. It started back in 1928, more or less, with John von Neumann with this paper on the theory of games of strategy. Before that, it was not a fully established field in mathematics. So why is it a field itself? Well, because a game is an interaction between rational players that want to achieve some goal. So you think of a game like that, so you have your mathematics to model that. So game theory studies games as chess, rock, paper, scissors. Guess 2/3 of the average is just a game. But it has also several applications on modeling human and animal behavior. For instance, it's fairly used in trading and markets. It's also used in diplomacy, biology, etc. So on that, I would advise you to watch this film. It's a very nice film. It's called A Beautiful Mind, Una Mente Maravillosa, with Russell Crowe. And it tells you the life of this mathematician, John Nash, that did some studies that led to the fully development of game theory. And he got a Nobel Prize in economics as well. So it's a very, very nice film. So I'm talking about games a lot. So let's play. For the game that we're going to play, I need a referee and 2 players. I will be the referee, so I need 2 players to come, 2 volunteers, let's say. Anyone? It's a very easy, don't worry. Yes, come on, yeah, I need 2, so. Okay, come forward, thanks. You're more interactive than my students in Ireland. Come here, please. Thank you. So I have here 2 coins, me, the referee, heads or tails, okay? And I will give the players as well 2 coins, heads or tails. 1 for you, 1 for you. Then I will ask you to move there. You cannot communicate, please. No, you here, you here. You cannot communicate during this, okay? So don't look, please don't hint what they should do. Yeah, okay. So what I'm going to do is I will give the players these coins, input coins, okay? And they will need to give back to me the output coins, the pink ones, okay? How do you win, right? So you cannot communicate. When I give you the coins, you cannot look at each other. You will need to decide what you want to do, okay? Yeah? So how you win? Well, here are the 4 possibilities of input coins, head, tail, and all that. So how you win? If I give you heads and heads, you both need to give back to me the same coin, both heads or both tails. Is that clear? The same for this. Okay. Don't worry, we have time. I can explain again. So if one of you gets heads and the other tails, you need to give me again the same coin. And only in this case, when both get tails, you need to give back to me different coin. So you heads and him tails. Here is 4. So for these 3 situations, you win if both your coins match, okay? And in this last situation, if they are different. Yeah? Questions? Yeah? Fine? Okay, so what I'm going to do is you will look over there. I don't want you to communicate. I will give you coins, and please don't give them clues about what I'm going to give them, okay? Because you know how they can win. And you know, okay. Yeah. So I'm giving you this coin. I'm giving you this coin. Okay, and you need to give back to me the pink one with your choice. Whenever you're ready. Yeah? Yeah? Now look. Okay. Okay, give back to me that. I will give you, we'll play again. Okay, but you don't know how you perform now yet. Okay, give me it back. We will do it again. Here's your coin, and here's your coin. Okay, again, whenever you're ready, give me the pink one. Yeah, you ready? Please. Let's do it again. I like to torture, apparently. Okay, let's do it again. Yep, sorry, yeah, that one, yeah. So here's your coin, and here's your coin. Whenever you're ready. Let's do it again. For the last time. For the last time, okay? I promise, I promise. So give it back to me. Thank you. And yeah, give me this one. I will give you. Okay. Okay, you're done. Thank you for your cooperation. I'm sorry for you to be here. So, as we have more or less counted, they won twice out of 4 times that we played. So that's 50% of the times. Okay? 50% of the times. No matter how you do it, if I keep the setup like this, the maximum number of times that they can win is 3 out of 4. 75% of the times. And that's it. They cannot win further than 3 out of 4. Questions at the end, yeah. Yeah, I will explain later. So yeah, 75% of the time. However, what happens if they would have their coins? What happens if I give them as well qubits? Qubits are quantum bits or quantum coins. Okay? So in this case, they would also have their output coin, pink one, but in this case, I will give them these qubits in addition. And these qubits are prepared in certain state. Don't worry about the specifics. But in this quantum version of the game that we just played, or that they just played, what will happen is that when they get their input coin here, they will do some operations on their qubits. So some operations. And depending, the qubits have possible results, 0 or 1. So depending on the operations depending on their input coins, they would do some operations, and they would measure, they would measure their qubits to find if it's 0 or 1, okay? And depending on the result of their qubit, they would output either heads or tails, as we just did. So with this, okay? So yeah, when they perform their operation, they give back to me the output coin, and with this setup, under certain assumptions, they can win 86% of the time. Remember that without that, it was 75 with the use of quantum coins, or quantum bits, or qubits. The maximum winning probability of this game is 86% of the time. This is very nice because you can win more often than if you don't use quantum bits or quantum coins. The game that I just presented to you is called the CHSH game. Okay? This is just what I was explaining to you. The winning conditions, the no communication condition, that they cannot communicate while they are playing, and that with normal coins you win 75% of the times, and with quantum coins you win 86% of the time. And why is this called the CHSH game? Well, because it's based, this game, on the Closer-Horn, Shimony, and Holt inequality in quantum mechanics. This inequality was proposed in '69, and is very important. So let's give you 2 sentences about quantum mechanics. So quantum mechanics studies the smallest components of that form the entire universe. The thing about quantum mechanics is that very different and very strange phenomena happen there. And back in the 30s and 40s, people were not very happy about quantum mechanics, and even Einstein didn't believe that quantum mechanics was a good theory, that there was something wrong, it was incomplete. So when a theory when you don't believe that a theory is good enough, what you do? Well, you come up with some tests to test whether the theory predicts the experimental result or not. And this inequality, CHSH game inequality, was one of those tests. A test to find out whether quantum mechanics was good enough or not. These tests are also known as Bell inequalities. So for the game that we played before, remember 75% of the time is the classical maximum, to be the Bell inequality, but quantum mechanics can go beyond that bound. And if you're not very familiar with quantum mechanics, you might think that it's only on the lab, but well, of course, this inequality, the test was passed by experimental results and by quantum mechanics, and many other tests. So we have that quantum mechanics so far works very well. And yes, I said quantum mechanics is everywhere. For instance, a laser that is everywhere is one of the most quantum mechanical objects that you can think of. So it's in the scanners of the supermarket, in the DVD readers. I don't know if that's used anymore, but in many other applications and our daily lives, basically. So the LED lights as well, it's because we have a deep knowledge of quantum mechanics. We can develop this technology, and any other technological device that we use every day. So I said that this is the CHSH game. It's a quantum game. So what's a quantum game? Well, and why do we care about quantum games? Well, because some problems or some situations, it can be explained as using a game theoretical framework. For instance, as I just said, the CHSH game is based on this inequality in quantum mechanics. It's based on the quantum foundations. Can be this problem in quantum foundations of quantum mechanics can be explained as a game. So you have your players, your rules, your consequences, and your payoffs. My research is about quantum games in the theoretical aspect, and is based, to give you a flavor, on this inequality. But a quantum game is any game when we add quantum resources. Quantum resources could be quantum particles, qubits, qubits, whatever, quantum measurements, all of that. You might think, so yeah, you have your game, you analyze what happens, as I just did here. We said 75% of the time, and we arrived at with quantum resources, it's 86% of the time. So you analyze what happens in the game, and then you apply the results. Okay, so quantum games is fun subfield by itself, but it has applications in quantum computing, for instance, with quantum algorithms in complexity theory. There's some overlap with quantum games, because as I said, you can think of some problems as a game. It has also applications in quantum information, particularly in quantum cryptography. It's a very hot topic right now, in communication and protocols, and also in quantum foundations, in the concepts of entanglement and non-locality. If you want to play more, there's this version of the quantum tic-tac-toe, or tres en raya, with quantum rules. Don't worry, it's very simple, but you can play now online. This is the link, and you can even choose the language that you want, and if you want the full version with the explanations, or the instructor versions to have it, for example, as a workshop to try to explain to teenagers some concepts in quantum mechanics. And it's fun, more fun than the usual one. Okay. So I said, explained that my PhD is about quantum games. Maybe some of you are thinking about doing a PhD or already have it, so I wanted to say a few words about PhD. So a PhD is typically 3 or 4 years, depends. In France, I think it's 3 years, here is 4. Where I am is 4, so it depends. And basically, you need to work with yourself, by yourself, and your supervisor or supervisor on a topic of your interest. and what you want to do is you want to contribute to your field. A PhD has pros and cons, of course. The cons is that it's hard. Okay. Not going to lie, it's hard. It can be very lonely, especially in COVID times, but even without COVID, it can be very lonely. It can be frustrating at times. It's completely normal. And also, since you are working with a supervisor, the relationship that you have with them can affect your experience in the PhD. But there, of course, there's some pros that you learn a lot about the topic that you're interested in. You learn a lot about yourself. You learn how to manage your time. You meet many people, usually. You can travel to conferences, to seminars, to all of these things, and you improve your communication skills. That's very important for research and life in general, I would say. So if I have to summarize the PhD in a sentence, would be that it is an emotional roller coaster. So sometimes you're up, sometimes you're down, but for me, at the end of the roller coaster, I have enjoyed it. Might be not for everyone, but this is my experience so far. Haven't finished, but let's see. So my take-home messages for you today is that quantum mechanics is super strange, but it's super fun. Okay? Some very weird thing happened there, so I really like it, of course. And then that a quantum game is any game when we add quantum stuff somewhere, in the players, in the strategies, however, and that quantum games have applications in quantum cryptography, quantum computing, quantum foundations, etc. So that's it for me, but I'm sorry, when I finish a presentation, I need to tell a joke. I cannot help it, I'm sorry. I apologize in advance. So the joke goes as follows. Why did the mathematician spill her food in the oven? Because the directions of the recipe said, put it in the oven at 180 degrees. So that's it. Thank you for listening. I see there's some laughter that maybe, yeah, take your time for the joke.
Thank you, Victoria, for the talk. So if anyone has any question, raise your hand. Okay.
In Spanish or English, however you're more comfortable.
Yes, it's better in English because...
Oh, yeah, okay, yeah, so, sure.
Thank you for the presentation. I have a question. Is the coin game related to the Nash game theory or the prisoner's dilemma?
Yes, you can think of, okay, so when I was talking about the Nash, John Nash, somewhere, okay, so yeah, this man developed what is known as a Nash equilibrium. A Nash equilibrium is a solution concept. That means that every game will have a solution, if you think of a solution as a Nash equilibrium, in which no player wants to unilaterally deviate from that. So in the prisoner's dilemma, there's a Nash equilibrium that is not ideal, because they would be better off if they would deviate, but that's the rational solution. So in this case, the game theory that we use is even simpler. We just think of the payoff. So you win if that is fulfilled, and you lose if that's not. So in this game that I was explaining to you, what you want is to maximize the payoff, because they are playing both together. So they both win or they both lose. When there's some competition, then the concept of a Nash equilibrium plays more a role into defining the solution of the game. Does that answer your question?
Yes, thank you.
No problem.
Any other questions?
Yeah.
Do you run a simulation in your PhD, like agent-based model? I don't know. I was thinking about you can simulate a player like an agent that have policies and make decision, have a goal.
Yeah, in my case, it's more analytical.
Okay.
I'm just trying to maximize a function.
Paper and pen.
Sorry?
Paper and pen.
Mathematica, more or less, but yeah. Yeah, so far. But yeah, there's people who do this evolutionary game theory, so you need to take into account then in a graph or in a network, and you need to take into account that.
Okay.
Yep.
Thanks.
Any other questions?
And in quantum games, do you take into account the possibility that players can agree to have a certain comportment in advance?
Yes.
Of the game?
That's for the 75%. I didn't allow them to think about the game or to talk. If they would agree to say, okay, I will always output heads, and I will always output heads. So taking into account that the coins are probabilistic, 3 out of 4 times, you will get this. So you get this, and you will always be outputting this. So in here, you would win, you would win, you would win, and you will lose.
So does the maximum correspond to this situation where
yes,
this rule is not there anymore?
What do you mean?
I mean, we said before the rule that they cannot communicate, but the maximum does count that they can communicate, or no?
Yeah, that they communicate before the game starts.
Yeah.
Before they can be here and say, if you get that,
and
I will output this.
And does the maximum change if we continue to say that they cannot communicate?
During the game, yes.
Okay, and how much?
What do you mean, how much?
The probability, how much does it change?
No, the maximum is 75%.
If they communicate and they don't communicate,
so they start before I give them their coins. They are here together, and they can agree. But when the game starts, they cannot communicate any further.
Okay.
Yes, they agree before. Then they are separate, and they can. There's no way for them to communicate which coin they got.
Yeah, okay.
Does it make sense? Yeah?
Yeah, I was wondering if they cannot communicate before.
Oh, no, before they can, yeah. Well.
Okay, before they can communicate.
Before.
Okay.
I guess the question is, if they don't communicate, if they don't agree to do a thing, I mean, if the coins that they are revealing are completely random.
Then maybe it would be 50% because you would go 50, Yeah, I guess. The 50%. The maximum, yes, you can go below that, of course. Yeah.
Anyone has?
So, when you do a quantum version of this game, what kind of operations do you do on your qubits to achieve that 86%?
Yeah, in this particular case, it is enough to do a rotation. Okay, so the allowed quantum operations are unitary operations. We don't think about the currents or anything. But with this, if you do a rotation about the x-axis, so just a rotation in this plane, for instance, they can achieve the 86% of the time. You don't need to go fully general. With that, it's enough, and it's a bound that is optimal.
Okay. Anybody has another question? I would like to ask you one question. You told that is still developing all this theory, and I was wondering if there's any current nowadays application of this theory. If I mean in industry or in other fields that are not physics, that they are using this kind of rules that are different from the traditional probability or game theory?
I don't understand what you mean.
I mean, quantum game theory is different from the classical game theory, and I'm wondering if there's any application that is nowadays for this theory, because it's still developing, but if they had the time or an idea to apply it in nowadays problems.
Well, yeah, as I said, the theory is itself the same, but you just add quantum mechanics, and then you want to maximize something or see what happens. But for instance, in these applications, where is this? For instance, okay, so in complexity theory, that means analyzing how hard it is to solve a problem, and then you want to classify how hard problems are. For instance, there's a big result from 2021 that they use a quantum game, and they arrived at studying this game that a complexity class, some problems are equivalent to these problems. For instance, also in cryptography, you can think of communication as two players wanting to win a game, and then we have the eavesdropper, so they are kind of competing in this game scenario. Then in the concept of non-locality, which is what we just played, you can try to come up with, Bell inequalities. That means situations in which the maximum classical has a value, and then the quantum version has an upper value. So there's this quantum advantage, and this quantum advantage can be used to, for instance, generate truly random numbers, because we don't have a generator of random numbers, it's pseudo-random. But for that, you can use the Bell inequalities to have the games to achieve Bell inequalities that have some applications in other fields. Yeah, does that answer your question, I guess?
So thank you for the talk again, and we'll go to the next one.